Yeah, thanks everybody. It is early in the morning, but I have my coffee. I think I'm ready to go. Really appreciate the opportunity to speak with you all. And as you know, the world is changing fast, and I'm sort of at the front line. So we're going to cover some topics I think that'll hopefully resonate with the group, and I'm sure these are things that have come up throughout your meeting. But I'm really glad to see that there's a lot of focus on bias, which I think is a broad category, but has a lot of implications. So I'm going to talk about translation bias, potential fixes in imaging space, and then we'll talk about the thing that's on everyone's mind, a little bit about generative AI. So in general, we're starting to see a lot of need for the solutions that we're all hoping to build and deploy in the world. Right? There's a massive physician shortfall, and a lot of this is really not showing any sign of slowing down. At the same time, medical knowledge is increasing very fast. In fact, back when I was in medical school, medical knowledge was doubling pretty fast, but you could keep up pretty easily. But now medical knowledge doubles so fast that it's almost impossible to keep up, even in my small specialty. And then finally, of course, there's a large amount of investment in radiology AI in particular, of course, my space, but healthcare AI broadly, and we're expecting to see that increasing year over year, despite some of the macroeconomic forces. There are a lot of companies. I'm sure you've seen a lot of them. A lot of these I put on the slide. Some of them don't. I don't think exist anymore. But there's probably 5 or 6 to take the place of everyone that slowly kind of fades away. And so we're starting to see a lot of churn. But certainly it has a lot more to do with some of the topics I'm going to cover today, as opposed to the idea that AI, at least for medical imaging, isn't useful. In the US, we obviously have the FDA, which regulates medical devices and has been pretty clear for at least our work that anything that touches pixels, of course, that's pretty much everything in radiology, would need to be regulated as a medical device. And I know that there's some different perspectives and different regulations between the different countries. I'm sure that are represented in this group, but nonetheless, I think there's a common theme that these need to be regulated as medical devices. And for the most part, when these solutions are approved, they're kind of frozen, right? It's frozen like software. And that raises some challenges that we'll get into. So I think a lot of people kind of assume that we're on our way, right? That with all these companies, all these FDA approvals, that we're doing really well. But I actually feel like we're not as far as we think we are. And that's not necessarily due to the technology. It's often due to the implementation, governance, and change management, right? That involve in that. Some of that's education, which we'll get into, and some of that's just that healthcare systems were not initially built for the solutions that we're building, right? Some of that's related to the workflow, some of that's literally the technology. So we'll kind of talk about what we can do to make this transition better. There are a lot of barriers right now that sort of kind of get folks kind of stopped in their journey. They built a great solution, they have a great idea, they think they're going to provide value, and then they kind of hit a wall. And then on the part of the healthcare systems, they have to deal with choice, right? There's a lot of these different models. Some are made by their friends in the academic center that they're affiliated with. Some are made by the startups that maybe they're sort of getting lots of emails from saying, hey, you should try our awesome new AI. And it's difficult to make that choice. Validation is a big problem too, right? How does it work in your practice? How are you sure that it's going to perform the way that is claimed, either from the lab data or from the sort of FDA or regulatory filings? And when does it fail? That's what we're going to talk about today. And then finally, integration, which that could be a whole day of talks in and of itself, right? And where I currently work at Nuance, so we've been integrating medical imaging software and solutions for 20 years, and so there's a lot of learnings there, right? And it's a lot more difficult than I think people recognize coming from the outside in. But I want to point out just kind of one of the first big problems that we're probably going to be encountering more and more, and it's something that I've been sort of calling the day two problem. So you can imagine that on day zero, you might do an implementation test, and your performance might be great, right? Like it might be just as good as, and this is a fictional example using a chest X-ray algorithm, just to make this discussion make sense. And so you might test it in your institution, and it may be great, right? The AUC is what you expect. That's kind of what's represented here. But then let's just say for the sake of argument that you've implemented it, and then a few months later, you may have heard from a radiologist that the models missed a few things or is not they're not agreeing with it. And so you might go back and do an audit. And as you know, that's a lot of work, right? You have to curate ground truth data. You have to run it back through the model, and you have to do confusion matrices or other analyses in order to determine how it's doing. So in this hypothetical example, maybe you do that, and for some reason, you're surprised to find that the model performance is decreased. You have, again, same model, but you have no idea why the model performance has changed in your practice. This is not outside the realm of reality. And what you want to know is what happened in between, right? You want to why did it change? And then you also want to know, well, if I did the audit today, but what's going to happen? Do I have to do an audit every day? Like, how do I as someone responsible for patients and a practice, how do I make a decision? Do I just cancel the use of the model? Is there something implementation wise that's going on? What's happening? And the reality is that we just don't know. People spend a lot of time getting through that really difficult implementation barrier, and then they don't have often a plan for understanding performance after it's been deployed besides feedback, right? And all of us are busy. We don't have time to give you feedback on every single model. And if you have 10, 15, 20, 50 models in your practice, it starts to get really, really complicated. So what you'd like to know is you'd like to have a direct understanding of performance over time, right? After you've deployed, you want to know that because there's lots of things that we recognize that can bias the model to kind of go off the rails in terms of performance. So you might install a new X-ray unit. Maybe it's a brand new system that has a completely different reconstruction kernel. You might have bad protocols. You might have hired someone who isn't performing the exam correctly. You might get rid of that person, right? And you could see the performance improve again. And then in this hypothetical example, you could have a whole distribution shift, right? Where a new disease comes up and the model has zero labels for that particular problem. So you can imagine all these things are difficult. And then this is just a toy example. There's many more that you can sort of concoct that could cause a model to drift and to change. And the key understanding is that most healthcare use cases, whether it's imaging or sepsis or something else, you often don't have a ground truth at the time that the model's making a decision to get that feedback. That's number one. And number two, again, those audits and to get that ground truth is super difficult, right? You have to do a lot of work to label and to really understand what the ground truth is. And as we'll talk about, there's also cases where ground truth may not be known for months, right? And so what you tend to see from a lot of folks is that this is the whole pipeline, right? That people talk about, okay, we build the model, we evaluate the model, we scale it, we can even test it on the place where we want to deploy, and then we deploy it. And there's this step that everyone seems to be kind of ignoring that is conveniently ignoring, that we need to be able to understand how it's doing after you deploy it, right? And there's not a great deal of work that's been done, and it's really that monitoring observability. This is best practices in every other vertical that I've looked into, right? Why do we not have this for our medical imaging AI solutions? And I want to give some credit to a group. There's a lot of groups working on this kind of problem for, again, other verticals, particularly machine learning that can be updated, which we'll talk about. But this group called evidently.ai, I really like a lot. Feel free to check out their site, a lot of open source work on monitoring. But it's a really, really great diagram to see what we're dealing with. So healthcare IT, they're used to software, right? They're not used to stochastic models that might change their change in performance over time. And so they can monitor if the model's working, like is it receiving images, is it sending inference back? But what we can't do in health IT is really understand all these other problems that are raised when we deploy these solutions in practice. And that's what we have to monitor. Of course, that's ML ops, and that's a whole other discipline that, you know, most of us spent our careers building and staying in the machine learning space. We haven't spent a lot of our time. We don't have a lot of experts in the healthcare ML ops workflow. So again, we can tell if it's working. These are simple metrics that are used for every kind of other software, but we can't tell whether the model's getting the data that it's supposed to. And we can't tell you in real time whether the model's predictions are right. And these are core principles that are part of the ML ops world, right? Is understanding drift, understanding outlier detection, understanding underperformance in certain segments, et cetera. But, you know, there are ways to monitor, so to speak, right? We can do periodic audits, as I mentioned. That's incredibly painful, but you can do that. You can do, you can use reporting tools. So in other words, I can use NLP on the report and compare that over time with the AI results, if that makes sense. So I can understand what the radiologist said, and I can compare that over time with the AI output. So that would be what I would call agreement, right? You're monitoring agreement between the radiologist and the AI after the fact, but over time. So if you see a change, that might cause a problem. But it doesn't really work in all these situations. Number one, the NLP could have noise. Number two, radiologists, as you know, we disagree with each other, right? Up to 30% of the time. And then finally, we are seeing more and more superhuman AI solutions that do things that I can't do as an expert radiologist. There's things that can tell me the body composition to the 5th decimal point. There are things that can tell me the quantification of lesions to an accuracy level that I can't do. There are things that can infer outcomes from medical imaging examinations. I have no idea how to do that. I can't tell you someone's 5-year prognosis for a lung nodule, right? And so how do I use agreement when I have these, you know, advanced AI systems in my practice? It's not going to work. So what we really want to do is we want to be able to compare what the model knows, right? What the model's been trained on, what it's expecting to see, with what it is seeing, right? And then be able to track that over time. In other words, I don't really need to know who's right, who's ground truth. I just need to know, is the distribution of things that it's seeing and a couple other metrics that I'll show you, what is it expecting to see? So that if it's working really well on day one, but I see a big change in the data that's coming in, I know I might have a problem. So if we don't have the ground truth available, we need to be able to check drift across a few axes. And the nice thing about medical imaging is we have some options here. We can look at the input data, right? We can look at the demographic. Everything in the DICOM header has a distribution, right? And we can compare that distribution over time. We can look at some deep learning approaches to this, which I'll tell you how we solved it using a deep learning approach on the pixel data itself. Okay. And then finally, we can look at the predicted probability. So if my model on average says there's 15% of the decisions are pneumonia with a 90% confidence, and then all of a sudden I have a 30% distribution of a pneumonia with a 10% confidence, or, you know, however you can adjust those numbers, that's a change, right? That's a change that I can see and I can measure over time. So what we've done is we've kind of taken each of those 3 input data sources that does not require ground truth at this point, and we put them together statistically into a one metric called the multimodal data concordance. It's kind of a bad, we probably need to come up with a better name for this. But what it does is it's sort of taking the DICOM data, it's taking the output predictions, but this is the key piece in the middle for the pixel data. We've chosen to go with a variational autoencoder where we can kind of encode the image down to its latent space, the least data that it needs to know in order to reconstruct that image faithfully, but using a variational autoencoder instead of just a traditional, so that we have that distribution in the sort of bottleneck part of the model. And that's actually where we can measure that latent vector distribution compared to the latent vector distribution of the data that the model was trained on. And that's another great population sort of distribution comparison, right? So we can look at how the pixels look, right, to the model, and we can see that over time. So it sounds great in theory. Does it really work? Well, we've got a lot of evidence that it does work. So we took a data set that had ground truth over time, over a long period of time, and we were able to look at our actual accuracy here, right? You can see how the on the left here is the actual performance over time. And then at point A, we intentionally broke the model. We intentionally changed the data set over time so that the performance got worse. So we changed it here by 3%. We changed it here by about 10%. Okay, so this is the ground truth over time. Now what we want to know is, since we don't have ground truth in real life, how would our metric work tracked against this ground truth? And what we found was that our model this metric could track the change and notice that, hey, you've changed it 3%. Performance-wise, you wouldn't know that, but this metric would know. And it could show that there's been a sharp decrease or change in the data that it's seeing versus the data it's expecting to see. And that's kind of how we're looking to track change or drift over time. So we've called this check stray. We have several papers coming out, and obviously this is open source, by the way. This is not I'm not trying to sell you anything. This will be available as part of some of the Microsoft Azure ML model monitoring solutions, particularly the things we're building for healthcare. But you can feel free to check this out. There's a GitHub repo, et cetera, to look at how you might incorporate this approach into model monitoring. And again, we don't want to just throw it out there. We want to actually have a fairly easy implementable solution for doing something like this. So we can look at 30, 50, 100 models and just kind of see, has anything significantly changed over time as we're watching them. And we want to be able to send up alerts, and we want to know not just that it's changing, but why it's changing. And so again, because we're looking at these different aspects of the input data, we can actually precisely say, well, it's actually drifting on this axis. It's based on the protocol. It's based on the machine manufacturer. You bought a new scanner from a different vendor and it's changing the model's performance. Disease prediction, confidence of that, all these different matrices can be measured over time and then investigated. So the way we're looking at this is being able to provide healthcare systems the ability at a high level to track models. Now, this is specifically for medical imaging because that's a difficult problem, but you can imagine that the same approach can be used for sepsis or mortality prediction, other things as well. But ideally, we want to make sure we have something for our pixel data because it is more complicated to track. Okay, so I'm going to mention a couple of things, and then hopefully we'll have some time for questions. So if we're able to monitor, that's helping us feel comfortable and that we can deploy these things at scale, right, in our health systems, and be able to feel safe that if there's a change, we can check on that. But it really gets down to governance, right? Who's gonna own this? Is it going to be the radiology department? Is it going to be the hospital system? Is it going to be the individual clinical departments that are using AI for their own use? So neurosurgeons might use AI for imaging for their own clinical use that have nothing to do with what a radiologist would want, right? That's happening everywhere, as you know. So it makes it kind of messy for governance. But then now there's one more thing that makes things really messy. And that's sort of the rise of the generative AI solution. So if you think about something like ChatGPT, right, which is increasingly available to anyone, right? And the ability for anyone to potentially use these solutions, whether or not your health system said it was okay, right? Using it on your cell phone, using it on your desktop computer, starting to play with it. And, you think you might be, okay, well, it's just text to text, we're fine. But with the number of users now adopting this solution and playing with it and learning about it and interacting with it and becoming familiar with the capabilities, we're seeing now the multimodal GPT-4 becoming a real possibility for use in a healthcare system, right? So if I can take an image of some ingredients, if I can take an image of really anything and interact with it, chat with it, you can imagine that we can get to a place where you can have a logical thing. And these are just examples from the OpenAI group, where they're taking pixel data and they're having second, third, or fourth order logical conversations with that image, about that image. And it's clear that the model understands that. But you might say, Matt, I don't think these models know enough about healthcare to really be used widely, right? By our patients, by our clinicians, by just anyone off the street. And of course, I think you know that's not the case, right? So we've seen just a couple of days ago even that these models are very, very, very capable in healthcare domains, right? So this is again looking at in the U.S. our qualification examinations for practicing medicine, and GPT-4's capabilities are another phase transition in capability in healthcare, right? And these are not simple questions. These are multi-step questions. They may involve multimedia, tables, charts, images, et cetera. And these models are doing better than humans, right? We've also seen from other groups that the models can answer questions, medical questions, to almost to the level of a human clinician, particularly when judged by clinicians. So what I'm trying to say here is that people are going to be using these things in healthcare, whether they're your clinicians, whether they're your patients, whether they're, again, other folks, right, other stakeholders. And we have to figure out how this is going to impact our practices and the use of AI. Because the issue for me, and I'm sure you guys have thought about this, is that the hallucinations are not zero, right? And we recognize that with a stochastic technology like this, that you can be fooled into thinking something's right when it's not. And so how are we going to govern this, monitor it? How are we going to actually use it in healthcare effectively? And then when we think about medical imaging, we've seen examples of where the model gives bad advice that sounds convincing, but even worse is that it has a terrible performance for medical imaging. This is what the model thinks a CT scan of the chest looks like, right? But we also know that things are moving fast. Things are moving very fast. I don't have to tell you that, right? And I'm seeing all kinds of stuff. And one of the things that we've already learned, I think many others have shown, is that despite the fact that these models don't have a great comprehension of medical imaging, it doesn't take many examples to teach them what medical imaging looks like. So we're rapidly entering a world where all the things that we've been building and doing, these narrow models, are kind of starting to sound a little bit old-fashioned, and it looks like we're moving towards the potential for general AI, right? For medicine and even for medical imaging potentially. And how might this work? Well, you can imagine that someone can propose taking healthcare data, which the model at this point has really only seen some open stuff, some PubMed articles. It hasn't really seen medical data at scale, particularly medical imaging. And you can imagine that there will be groups, many groups, hundreds of groups around the world that will take healthcare data, fine-tune, or frankly, even train a foundation model, and then be able to have different prompts or interactions or APIs that interact with all kinds of different users in healthcare. This is not science fiction anymore. And so what does this really mean? And for me, no matter how good these models are, there's still some drawbacks. Part of it's because I've been spending a lot of time in this space. Many of you would recognize, you could list off 10 different reasons why it's not necessarily going to be perfect. But that's a problem for us, right? As human beings, we have automation bias, and that is absolutely a problem when we're trying to take care of patients and we're trusting the outputs of some of these models that can go off the rails, right? And I like to use the analogy of the GPS, right? So you probably haven't used a map in about 15 years. And so, a lot of folks trust the GPS no matter what, right? You turn right, you turn right. But there's a lot of examples where people trust that model, or in this case, the GPS, and do terrible and frankly dumb things like driving a car on the train tracks. And there's a phenomenon, death by GPS. That's a thing. We all as humans have a inherent predisposition to trust the automated systems more than our own common sense, right? And this has been shown time and time and time again. And as we have more automated systems moving into our worlds, into our lives, into our practices, we can see a situation where bad things can happen that again, should have been anticipated, but there's no way that we have right now to deal with that. And so in healthcare, this has happened many times. Every time a new technology comes around, we have examples where healthcare has had this problem. And back in the EHR days when they were just introducing EHRs, there's a great example from this book by Bob Watcher, where someone entered in a dose that they wanted to give to a patient in the medical record. Unfortunately, they entered it in the field that said weight-based dose instead of the actual dose. And so they gave a patient 6,000 milligrams of an antibiotic. Now, this wasn't just one person that had automation bias. This was the resident, the attending physician, or the consultant, I think you call it out there, the pharmacist, the nurse gave it, and the patient even took, multiple pills because that's what the system said the dose should be. So this is a failure of our own biases as humans, and that a lot of that has to do with our understanding, our technical literacy of how these systems work. And of course, we see that a lot less frequently now, right? We recognize these machines can make mistakes, but I don't want to have to see patients suffer because we're learning how to use these technologies. And so I have increasingly seen, and many of you agree, that physicians are typically some of the least clinically knowledgeable because we have other things to learn and do. And we're starting to feel overwhelmed with the technology. And that was before GPT-3 and 4. So what we really need to think about critically in our systems is how do we educate our clinical users? Because this genie's out of the bottle. It is coming into your systems, whether you do it through one department or whether someone walks in the clinic with their phone. How are we going to educate them so that they understand where these tools might be great and where they might not be, and to always be thinking about the possibility of things like hallucinations and biases and errors? I've spent a lot of my career doing this, trying to teach these concepts and principles without coding and math. It's a lot easier now when you can code in natural language and people can learn. And a lot more people are getting familiar with using these tools outside of the clinic. We've recently updated our course to include all of the kinds of things that are coming up now with foundation models, how they work, where they fail, where healthcare they might work, where they might fail. But that's just one part of the solution. I think it's kind of meeting halfway, right? We're teaching the models healthcare, but we also need to teach our clinicians about these technologies. So wrapping things up, I think we have two worlds that are colliding, right? We have all of these narrow solutions that have been built for years and are kind of making their way into the world. And how are we going to deal with them? How are we going to use them effectively? How are we going to monitor them? And I think hopefully I've provided some ideas on how to do that. But at the same time, we're having this influx of generative AI, which is going to permeate our society in every interaction that we have with an electronic system, at least the way things are going. And we need to make sure that we're well prepared to educate and understand our own biases and challenges around using that so that we don't cause any patient harm. So that's all I have. Thanks so much for having me out here, but I think we're well on our way to completing this project of using AI effectively for our patients. Thanks so much, guys.